Hello everyone, I'm Wang Lei from Alibaba Group. I'm very glad to introduce our work on GNN training, FlexGraph, a flexible and efficient distributed framework for GNN training. Here, flexible means that we propose a new programming abstraction for GNN models, and it allows developers to express different types of GNN models easily. Efficient means that FlexGraph outperforms other state-of-the-art GNN frameworks. Next, I will introduce these two parts respectively. First, I introduce a flexible programming abstraction for GNN models. Most GNN models fit into the neural multipassing framework, where the computation of each GNN layer includes two steps. For each vertex in a graph, it first aggregates the features of its labels to compute its neighborhood feature. Then it combines its own feature with the neighborhood feature to update its feature. By investigating state-of-the-art GNN models, we find that GNN models have diverse definitions of labels and neighborhood aggregate schemes. Next, we present a new two-dimensional classification for GNN models according to their neighborhood definitions and aggregate schemes. The first class is DNFA model, direct labels with flat aggregation. Direct labels mean that the neighborhood of each vertex consists of all its one-hop labels, and flat aggregation means that the aggregation function only performs a single-step operation. GCN is a DNFA model. Consider vertex A in a sample graph. In each layer of GCN, the labels of A are D, E, F, and H. To produce the neighborhood feature of A, the aggregate function just sums the features from the labels of A. The second class is INFA model, indirect labels with flat aggregation. For INFA models, a label of a vertex can be a vertex from a nearby subgraph instead of its actual one-hop label. Similar to DNFA model, neighborhood information is gathered in a flat manner. For example, PinSage is an INFA model. It has a similar architecture to GCN. However, PinSage adopts an importance-based neighborhood definition. The labels of each vertex is defined as the top k visited vertices in several random walks starting from it. If k is set as 2, the labels of A are C and G, since C and G have the highest fitted counts. Both C and G are indirect labels of A. The third class is INHA model, indirect labels with hierarchical aggregation. In an INHA model, a label can be any graph structured data. In the neighborhood aggregation, multi-step operations are allowed. MAGN is an INHA model. In MAGN, the labels of a vertex are set of metapath instances. Each instance has a type called a metapath. Each metapath is an ordered sequence of vertex types. In this figure, vertices of different types have different colors, and we have two metapaths, MP1 and MP2. As a result, the labels of A are P1 to P5. The aggregation operation of MAGN is performed in a hierarchical way. When computing the neighborhood features of vertex A, MAGN first computes the features of each instance by combining the features of vertices belonging to the instance. It then combines these features of the same metapath type to compute the features of MP1 and MP2. And finally, it aggregates the features of MP1 and MP2 to get the neighborhood features of vertex A. Inspired by the vertex-centric program models like GAS used in the graph processing systems, some GAS-like Program models for GNN have been proposed. Saga-N is proposed in layer graph. The computation of a GNN layer is divided into 4 stages: scatter, apply edge, gather, and apply vertex. To compute the neighborhood features, each feature first scatters its feature along its outgoing edges to produce a feature for each edge. It then applies NN operations to generate new edge features. At last, each vertex gathers features of its incoming edges and combines them as its neighborhood feature. At last, each vertex assembles its neighborhood feature and its own gold feature to compute its updated vertex feature. In Saga-NN, each vertex computes its feature by combining the feature of its one-hop labels in a flat manner. It's hard to express NFA and NHA models using Saga-NN. To solve this problem, FlexGraph applies a hierarchical dependent graph. The HDG for each vertex contains 2 parts, a schema tree and a set of neighbor instances. The schema tree encodes the hierarchical tree structures for label types defined by the GNN model. The label instance is a set of labels defined by the model. Each label instance is linked to a leaf in the schema tree to encode its type. If a label instance is beyond a single vertex from an input graph, then HDG collects all its associated vertices in the input graph to the instance. Based on HDG, we further propose a new GNN programming abstraction, NAU. NAU introduces a label selection stage to build HDG. Having HDG in place, in the aggregation stage, NAU asks the user to specify an aggregation function as a UDF for each level in the HDG. Then NAU automatically performs the hierarchical aggregation by applying this UDF in a bottom-up fashion. Finally, the update stage combines the old features and the neighborhood feature and outputs real features for the next layer. Next, we outline the sample implementations for GCN, PinSage, and MAGN in the NAU model. In the label selection stage, users only need to implement a UDF for each label type. In the aggregation stage, users need to provide an aggregation function for each level of HDG. With the NAU in place, next we introduce some optimizations for GNN training. The first is hybrid execution, where FlexGraph adopts different aggregation operations for different levels of HDG according to the properties of different levels of HDG. Take the HDG for MAGN as an example. Each vertex at level 2 has multiple incoming edges, and we adopt the feature fusion operation at this level. Each vertex at level 1 has only one incoming edge, and the sparse tensor operations are used for this level. Finally, all root vertices at level 0 show the same schema tree structure. At this level, dense tensor operations are applied. Next, we introduce these 3 types of operations and why we choose different operations for different levels. The first is sparse tensor operations. To aggregate the neighborhood features using sparse tensor operation, each vertex needs to send its feature to its outgoing edges as edge features. Then each vertex collects its neighborhood features through its incoming edges and applies a user-defined aggregation operations. That means edge feature has to be materialized. Consider vertices at level 2. Each vertex at level 2 has only incoming edge, as each label instance has a unique label type. Such operation will not need to the feature of each vertex has been materialized many times. The second is feature fusion operation. Each vertex at level 2 has multiple incoming edges, and the sparse tensor operations will result in huge memory overhead as the feature of each vertex has been materialized many times. To solve this problem, in feature fusion operation, each thread first loads the features of vertices at level 3, then performs the aggregation and appends the results to the buffer with respect to destination vertices at level 2. The third is dense tensor operation. Dense tensor operation is very efficient in current NN frameworks, but it requires a regular form of the input. This is fully satisfied by the schema tree, as all root vertices share the same schema tree structure. The next optimization is workload balance for distributed training. Existing solutions use different graph partition algorithms on the input graph to solve this problem. However, as we can see, the input graph cannot capture the dependency information among vertices. Therefore, our method is performed on a new induced graph. This graph is created by collecting roots and leaf vertices in the HDG. In addition, instead of using static metrics like vertex weights or edge weights, inspired by application-driven application partition, our method allows user to provide a UDF to define the computation cost of each vertex. Finally, we report the performance of FlexGraph. First is the performance in a single machine environment. Among all baseline frameworks, FlexGraph can achieve the best performance, and only FlexGraph can support efficient training of MAGNN. The next is the performance in a distributed environment. On all 3 GNN models, FlexGraph nearly achieves linear speedups as the increase on machines. That's all. Thanks for your attention.